Okay, for change of pace we're going to look at some predicting reactions, which at this point we have not done on one of these screencasts here, and I picked this particular one because the questions I have on this are some of them are more common ones, so some are oxidation reduction, precipitation, acid base kind of things that we're going to see consistently. Okay, so for part A it tells us chlorine gas, an oxidizing agent, is bubbled into a solution of potassium bromide at 25 degrees Celsius, which means room temperature. So for part A, they give you a big hint as to what type of reaction it is. They tell you chlorine gas is an oxidizing agent. So not only do they tell you what type of reaction it is, they tell you what's going to happen to chlorine. So since chlorine gas, so we have Cl2, is an oxidizing agent, that means it's going to be reduced. So in terms of your oxidation states, always for a neutral compound like that, or a neutral molecule, neutral atom, chlorine, it's going to be 0. And so if it's reduced, it's going to go to some kind of negative, so it's going to go to its ion form. So chlorine gas, and it's going to be reacting with potassium bromide again. And so again, with these predicting reactions, we only care about the net ionic equation, and the bromide is the one that's going to be reacting. Potassium is not going to be part of it, so we're going to have Br minus. Okay, and so what's going to happen is they're kind of going to trade places, where chlorine is going to be reduced, bromine is going to be oxidized. So chlorine is going to form your ions, Cl minus, and what happens, you get Br2. Okay, and so that's what happens, is that these kind of switch places like that. One starts as an element, goes to the ion, and vice versa, and then the last step we need to balance it. So 2 Brs there, and 2 Cls there. Okay, so we get 4 points. And that's for the first part, and then they always ask this little random question here. And so with this one, it's asking you to predict the sign of delta S for the reaction and to justify it. And so again, anytime we're predicting delta S, we're looking at two things. We're looking at phase, and we're looking at number of molecules. So if we increase the number of molecules from reactants to products, that's going to tend to increase our entropy, because again, more molecules, more disorder. The other thing we're going to look at are phases. Okay, and so what's going to happen with phases? So for example, a gas has much more randomness than a liquid. Where being in a liquid form, there's a lot more order to it. Okay, so chlorine at room temperature, and so I think the reason they included the 25 degrees is to tell you that it is at room temperature. So chlorine's a gas, bromine aqueous, chloride aqueous, and then bromine. The difference between chlorine and bromine, a big difference, at room temperature, bromine's going to be a liquid. Okay, both London dispersion forces, this is just a little bit bigger, it's more polarizable, it's going to have higher intermolecular forces, and so same temperature, it's going to be liquid as opposed to a gas. And so from here we're going from something that has higher entropy to lower entropy. And so the question is predicting the sign. And so what helps with that, and if you're a little unsure about that, take a look at your equation sheet here, where it tells you your delta S is products minus reactants. Okay, so if our products have lower entropy than our reactants, that means that our delta S is going to be negative. Okay, so delta S is going to be negative in this case. Okay, again, because of the difference between absolute entropies of a liquid and a gas.